several conversations with Todd Burton and his people at the City of Brandon, because they were looking at deploying some digital radio systems at that time and stuff. So we kind of started the project, a similar project last year, and it kind of fizzled out. But we were great to see Guillem kind of show some interest in it this year, and come up with a kind of a new twist on a kind of a use of these radios and see what we could do with them. So this project is very much about understanding the capabilities and the uses of digital VHF radio. So with that, I will turn it over to Guillem. His will be about a half-hour presentation. So we'll do the presentation questions, and then we'll move into some of the other shorter presentations after that. Guillem?
Good. Okay. Welcome, everyone. My name is Guillem Co. I'm a communications engineering technology student. And today, our friend Murphy visited us, and my laptop just died. So I had to rebuild the system on another computer, and the stupid Windows 8 didn't work with the drivers. So I bring my laptop from my desk, but now it's good, it's working. I will have a full presentation for you. Sorry. My project is about digital VHF radio applied to machine-to-machine systems. As Grant said, this project started last year as a part of a fleet monitoring system, but I found that was already similar products on the market that were doing the same and even better, like with years of experience and development with professional engineers. So I decided to look for a new focus on the project. So I decided to apply this system for machine-to-machine communications. First of all, what is machine-to-machine? Machine-to-machine is a very broad term that the people love to use and refers basically to communication between two devices to obtain certain degree of autonomy from each other and the users. So that way the user doesn't have to be in every step of the process. If not, the device communicate between themselves and they are smart. The main system used for this kind of technology for machine-to-machine is cellular, because we already have a very existing network. The devices are low cost and they have low power consumption. But sometimes another examples of machine-to-machine could be satellite, Wi-Fi, Bluetooth, serial cables. Zigbee, as my classmates show you, is another type of machine-to-machine. But sometimes we need this kind of communication in area where we don't have cell phone coverage, and if we don't have cell phone, obviously we are not going to have any Wi-Fi, or maybe it's hard to get a link with microwave because it's too far, or there is some obstacles in the line. And then imagine you have a farm or you have some cattle 30 kilometers from here, and you have a gate or machine that you want to turn on or turn off depending on some variable, for example, from the temperature or some other variable that you want to check, and you don't have cell phone coverage. Your alternative probably is use satellite, but that's gonna have some delay in the communication because you have to go up and down, and you are gonna have to pay a pretty expensive monthly fee if you want to switch it a few times a day. That's gonna be huge. So here it's when my new focus for the project came. Why we don't use our existing VHF systems applied for machine-to-machine communications, and if we want to control a device, we just hooked up to our radio and we can control it remotely. So the benefits of the VHF is very important. Is a very important band. It compilates the frequencies between 30 megahertz to 300 megahertz. And it's very important because it's the first frequency that is realistic to use the antennas for portable devices, such put it in cars or in handheld devices. Lower frequencies have too large wavelength to be able to use realistically. But at the same time, is one of the lowest frequencies we can use in our portable devices. So still having properties such can penetrate buildings and trees, and the distance doesn't affect as much as other frequencies such as microwave. And why to choose digital over analog? Well, analog is great for voice communications at short distance because it transmits everything the microphone gets. But as you can see in this graph, the analog signal drops when you lose the signal, and at some point you lose it completely. The digital signal, it's going to have a more artificial sound because it's compressing your voice, it's sampling your voice and compressing it and sending it. So as you can see at the beginning, it's going to sound not as great, it's not going to be hi-fi. But using digital signal processing techniques, you can correct the errors of the signal and keep having like a very good signal despite that your signal is not as strong. Another advantage of the digital technology is that because you're processing your signal, so if there is some cyclic sound such as an alarm, a buzzer, or some noise that you don't want in your system, the digital processing, it's going to be able to detect that and don't transmit it. So that way, if you're talking in a very noisy environment, the communication is going to be way better because this noise it's going to be reduced. Also, digital signal allows encryption, so if you're concerned by the security of your data, you can encrypt and have a robust system. Also, another point that I really like from this technology is that VHF is similar, means ultra high frequencies. It has similar characteristics to VHF, but higher frequencies, and the propagation is not as good. And you can have repeaters connected to IP network using another backbone communication, such optical fiber or copper, and connect all them in a network. That way, you can have different sites covered by your base, several base stations connect at several hundreds of kilometers. And in this base station, you can have remote sites that can connect, networking each other. This haven't been part of my project, but it's an option to add in the future. So I wanted to explain you here. So in summary, the advantage to use a VHF frequencies for machine-to-machine, it's that we have low delay because we are creating point-to-point links. So we don't have to use a satellite or external infrastructure that could delay our signal. It's just we have two devices. That make it very good for remote locations and places where there are no existing infrastructure because you only need your base station and your remote site. You just have to make sure that the antennas are high enough and you have enough gain to be able to receive the signal. I test this system myself. I put the base station on the lab and I used the existing antenna mounted in the roof, and I had successful communication over around 38 kilometers. So I'm sure that there are areas way closer that you already don't have cell phone coverage, and that way in these areas, if you have some remote site you want to monitor, you will be able to monitor it. Another advantage is that if your company already has a VHF system, this is a very easy implementation. You just need the prototype and the graphic interface that I designed in my project, and you can use perfectly your existing system, and it's gonna be compatible with your existing voice channel. So in the same channel, you can transmit voice and data. If you really need a lot, if you have a lot of users and all of them are talking at the same time, or you have tons of data, maybe you should consider get another channel. But for this project, I only had 2 radios, so one channel was more than enough for me. And if you use this, you only have to pay a annual fee. That if you already have the system, you have to pay it anyways. So you're gonna save all the monthly fees for cell phone network or for satellite or whatever other system you're using. Okay, so my solution, this is the block diagram. We have a remote site where we want to control, and we have a base station. On the remote side, we have our radio connected to a microcontroller. The microcontroller is going to be the brain, and I'm going to talk more specifically about each part soon. The microcontroller collects the data from the sensor. In this case, because it was just a demonstrative purpose. I just selected a temperature and humidity sensor. I didn't want to go further in this field. And we have a relays. The microcontroller is connected to the relays and turns on or turn off. The relay works as a switch, and if the relay is on, your machine or device is going to be on. If the relay is off, it's going to be off. In the other side, in the base station, we have the other VHF radio that is communicating with the other. And we have connected a PC with running a graphic interface. This graphic interface is going to allow us to see the information of the remote side, as well as turn on or turn off each one of the relays independently. And also it's going to, all the data that is receiving from the remote side, it's going to be stored in a TXT file. This TXT file is in a cloud platform, so you can access from anywhere. So you can be away of your base station and keep seeing if there is any problem in the remote side. So the items to deliver in this project, I have focused in these 4 items. The first is the radio configuration. When I get the radio was in the lab. I know that had a 25-pin connector in the back, but I had no idea if it really was capable to send data, how that was going to work. So big part of my project have been investigate what you can do with the radio. The second part have been the MCU code. It's like the source code for the microcontroller that controls all the functions, be able to read from the sensors, be able to turn on or turn off the relays, store the information in a TXT file. Then the PC interface. The PC interface is going to be the face of the project. It's what the user is going to see every day, and it's going to use to see if the remote side is okay, or if it wants to turn off the machine, or whatever you need. And the prototype. The prototype has to be simple to be able to connect to the radio and be able to connect your machine. Cannot be too complicated to use for the customer, and that's what I intend with my prototype. The microcontroller unit, I decided to use microelectronica boards and a PIC microcontroller because they provide me with all the features that I need for this project. This project didn't really need a lot of processing power. It just needs some inputs, some outputs, and be able to process all this data. And the big microcontrollers, which I have experience working with, could that for me. So I just decided because that was a demonstrative purpose, and I was very interested in know what the radio could do. That was my choice. And the main functions the microcontroller is collect the data from the sensors and send it to the radio, and execute the commands received from the PC if have to turn off or turn on a relay. The PC interface have been made using LabVIEW. LabVIEW is a software from National Instruments that allows to program in a very visual way. Like it's similar to, I will say that it's a visual programming language. Yeah, because if you have a while loop, it's a mark where you put all your things inside instead to be writing text. It's visual. I never used this software, but had a pretty low learning curve. And mainly what it does, it receives the data from the remote side. It displays here. For example, here it's displaying the temperature, the relative humidity, and the status of each one of the relays. On the left, we have the configuration for the serial communication between the interface and the radio. And on the top, we have the 4 switches that are controlling each one of the relays. And if we want to refresh it immediately, we click the right latch. Also here we have a virtual LED that is going to indicate the state of the system. If the LED is green, the system is all right. If it's red, there is some problem in the communication. This is how it looks like, the LabVIEW. For example, this is all this is engulfed in a while loop, and this is a scenario. If it's reading, it's going to do that. If it's writing, it's going to do something else. In the configuration of the radio, I found out that the radio was capable to send data using several modes. The one I choose have been the transparent 2 mode, using the prototype NXDN from Kenwood. How this prototype works, it's the PC transmits the data to the radio. This radio buffers this data and modulates them. The modulation that is using in the digital system is for PSK, and then sends all the packets in a row. They had like a previous version of this that was the transparent mode one, and between each transmission of packets, the packets were only 80 bytes instead of 314, and between each transmission you had a little bit of delay. That allows to have a higher data rate and transmit much faster. So if you have a lot of data, your network is less busy. This is the prototype device I created. It has a LCD screen to show on the remote side the temperature and the relative humidity. It has a main switch where it can be on. Where if it's on, the device is going to be controlled from the graphic interface, and if it's off, all the relays are going to be off. So if you need to service any of the machine, you can do it without danger to get shocked. Here we have 4 LEDs. Each one indicates the stage of each one of the relays. We have the temperature and humidity sensor, and the device can be powered through USB or through a 21 millimeter barrel connector. And the connector I decided to use is the DB25 because it's the same that the radio uses, and you can use a regular cable, factory made DB25 male to female to use it. As I said, I wanted to be easy for the final user, and I didn't want to use special connectors or have to find an adapter for it. This is the inside of the prototype. Here you can see the development board. I use the Ready for Pick from Microelectronica. This is my microcontroller. And here is the LCD screen built in the case. Here there is the relays board, and all this is connected to the microcontroller that it's controlling everything. Here you can see the sensor, and here there is a little integrated circuit that is stepping up the voltage because the microcontroller board works at different voltage than the standard for the RS-232, and I need to modify this voltage to be able to use the serial port. My testing, I mainly had 2 different tests. The first one have been a closed loop test. That was to test the system under ideal conditions without any loss to distance or interference, and a field test where I mounted the remote side of my car, and I drive at several spots, and I check in a real application simulation what was the performance of the system. The results have been that under ideal conditions I had 99.27% of uptime, so I had some too many resets on the microcontroller, but besides where I'm going to explain you now. And I had successful communication over 37 kilometers. So I drive south and I check the signal at 7 points, and the edge of my communication was at 37 kilometers. So this was my setup for the closed loop test. I connect the radio back-to-back using a coaxial cable and a 40 dB attenuator to protect from overpower. The radios were in low power mode here. And in the one in the left was connected directly to the PC with running the graphic interface. And on the right we have the prototype directly connected to the radio that was sending the temperature and humidity data. And then the one on the left, the PC, was storing all this data for further analysis. This test ran up for 1,000 minutes, in which I had 1,990 transmissions. Each transmission have 3 different variables: the humidity, the temperature, and the stage of each model, and the graphic interface at a timestamp. That way I could know how many time I had between each transmission. The average is that was sending every half minute, was sending one burst with all this information. That's pretty close what I expected because I had that the microcontroller should send every 30 seconds. And also if the temperature changes more than 2%, like up and down, or the humidity, also it's going to send a refreshment to notify the user that is in the graphic interface. So I lost some of the 30 seconds, but I also recovered using the 2%. So I had an average of 2 transmissions per minute, approximately. I had 42 resets in these 1,000 minutes. In each reset, as much as the system can be down is 10 seconds because it's using a watchdog timer. So if something gets blocked in the system, it's going to reset for itself instead of stay like few minutes without transmission. And I had an average of 23 minutes between each reset. If we do the 42 minutes for the 10 seconds down, I had maybe 400 seconds the system down over 1,000 minutes. So that gives me an uptime of 99.27% of the time. So just say that 42 resets is a little too much. It's not affecting the system, but that should be revised. I especially have seen that when I was trying to send and read at the same time from the serial port, the microcontroller was resetting. So that's something that I should work a little bit further. But besides that, the system it's functional, and 99.27% of the time it's probably more than what we need. This is the setup for the field test. The PC with the radio were on our lab, and they were connected to the radio mounted on the roof. And I installed the magnetic mounting antenna on the roof of the car. I put the radio, and I had the prototype device. The prototype device was getting the temperature and humidity information and was sending through the radio to the base station that was being logged in the PC for further revision after. What I intend I had 5 established locations where I was going to test, plus an extra one that was the edge. So my locations were at 1 kilometer, at 5 kilometers, at 10 kilometers, 15 kilometers, 25 kilometers, and the edge of the transmission. In all these locations, I had good connection. The prototype was working good. But I have some spots that after when I revise the data that I receive, these are the red spots. The red spots are areas where, meanwhile, I was driving through and I had the system on, I found in my data a gap of data. That means that during this period, I wasn't receiving any data. Also, I matched this data with the terrain, with the elevation of the terrain, and you can see that I have these losses always after a hill. That's because the terrain it's blocking my signal. It's creating a shadow that it's not allowing my signal to go through. The VHF is great for buildings, for trees, but hill is too much. It's very hard to go through a hill with a radio frequency. Almost impossible. And yeah, here it's the edge of my communication. I here completely lost my signal because there is like this huge downhill, but by that level, my signal to noise was already 12 dBs, as I'm gonna show you. This is the curve of my signal. 1 kilometer, I had this signal and I went through. My signal was getting lost. The requirements for the system to work, you have to have around 12 dBs of signal over the noise floor. The signal is quantified in dBm. That's how many millivolts there are in the per hour, what you are transmitting, how much power that it has. And then there is like a noise floor that there is some electromagnetic noise always surrounding us. Here probably is higher than if we go at the country. But at that point I had 12.5, that was the edge of my communication. So maybe even if I didn't have my downhill, my communication would have stopped soon. Well, as a result of this test, I think that the system is pretty reliable and can be used for remote site monitoring. The recommendations I have for the future is try to, I would like to see this implemented with some new uses, because the way I design it is still viable to be used in fleet monitoring. For example, if you have some sensor in your vehicle or your bus that you want to monitor, can be attached to my prototype, and that can be sent to the base station and monitor for further revision. So if you want to track the alerts in your engine, maybe you have a device that collects this data and sends it through the radio. Further work that we should do, it's lower the transmission time, because as I said, I only had 2 devices, so I didn't really have any concern about time. But if you plan to use this on an existing system where you already have many users that can talk at the same time, or you have like a lot of sites, or from every site you need to take off a lot of information, it could create a collapse in the network and could not be very smooth. That could be achieved increasing the data rate. The radios are going to improve, and the data rate you can transmit and the modulation, it's going to improve as well. And also that could be improving the software performance, getting out of all these resets I had, and making it more efficient. I will also see this implemented with PLC, with programmable logic controllers that are the standard for controlling the industry, and connect all this to IP networks so we can have several remote sites with like huge distance. For example, in a natural park, we can have one central station that is communicating to the remote site, and we have somebody monitoring all the system in some more central location using a IP network. As a conclusion, the VHF digital radio is a viable machine-to-machine communication system as alternative for other technologies such as cellular or satellite. It has a various implementation for existing users that already have this system on the company. It is a solution with market, especially here in Manitoba. We have a lot of areas that are not covered by cell phone, and sometimes we need to have some monitoring or some control. And last point is that you can still sharing like your voice communications and your data communications under the same channel, so you only need one license. If you really have a lot of data or more people, you always can get more channels. Okay, so do you have any questions so far? Or do you want me to forward with the demonstration?
I think we should do the demo first, and then we'll...
Okay, sounds good. Okay. So right now, these computers have the graphic interface that I can show to you. So, can you see it?
Yep.
Okay. So here it's reading the temperature and the humidity from the prototype that is there, and also it's reading the state of each motor. As you can see, the first relay is off. The first relay is the one I have connected to the fan. I'm not using the other 3 right now. So if I turn it on and I click the right, the fan just turned on. Okay, right now I'm transmitting through VHF frequencies between the 2 radios, and I can control these systems. Okay, Alex, can you go in the prototype and breathe over the sensor, please? Breathe over it. Okay, you can see the temperature and the humidity changing. So if it changes more than 2%, it's immediately notifying and without waiting the 30 seconds. this setup, if you don't want every 2% because it's too low, you can put it 10% or whatever needs. This system, the good point of this system is that it's very flexible and can be adapted for the needs of each user. And as I said, I am still having voice communication. Hello, testing. So I'm using the same channel for voice communication and for my data. Okay. And if I come here, if I'm in the remote site and I decide that I have to service the fan, I can just turn off the switch and the fan is gonna go off. I don't really have to talk with the central. And meanwhile this is on, nobody can turn it. Meanwhile this is off, nobody can turn it on. So if I want to service the fan, I'm okay doing it.
Can you talk about some of the other like local notifications or displays on the?
Yeah, and well, here there is the LCD. You can see it blue. Probably you cannot read it, but here it's saying it's giving the temperature and humidity. Let's disconnect the cable with the radio to see what happens if our communication goes down. Okay, so this is set up that if it doesn't receive any communication for 1 minute, the display it's gonna show a message that it's gonna say link down, and it's gonna change between the temperature and humidity values of the location at real time, and this message letting know that the system is down. At the same time, on the graphic interface on our virtual LED, it's gonna become red, and it's gonna show us that the system is down. So if we just wait a moment. Meanwhile, do you have some questions I can start to ask? Okay, Ryan?
When you've lost your network, does that change the values of the relays, or do they stay where they were down?
They still in the value they are down. That's true. It's something I didn't explain. The microcontroller have a built-in memory, EEPROM, and every time I change the state of a relay, it's stored in this memory. So if the power goes down or the network change or you reset the device is going to reset with the last settings that you set up. Okay, so I'm going to put in the camera. Have this huge battery for the microcontroller. So here you can see in the graphic interface the LED is red because the link is down, and my microcontroller. Okay.
It's too bright.
Well, it's there you go. So it's showing the temperature and the link is down. So that way, if somebody in the remote side can know that there is some problem with the communication and be able to help to fix it. And to fix it, you just need to plug it on, and it's gonna work the same way it was working before. Okay. More questions? Yeah.
So when you open up the radio for voice communication, does it override the data feed that's going on at that time?
Sorry?
So if you're going to use it for voice, like if I'm going to hit the mic,
Yeah.
what happens if there's a data transmission in progress?
It's gonna take preference what you are doing first. The radio is gonna wait for several seconds to see if it can transmit, because the channel at the moment is busy. If you so if you talk for too long, it's gonna dump the packet, but because of this system, it's not really a concern, because if it's something going on, it's gonna send more updates, because with the 2% change, and if not, every 30 seconds, you're gonna receive a new notification. So it's very difficult that everybody is gonna talk at the same time this is transferring, because all it takes to transfer is 2 seconds or maybe less. It depends on the packet. So it's very easy that gets fit in the network, and then you can keep talking. Yeah, maybe between the key between you and the other, it's gonna transmit the data, and the other person is gonna respond to you. Yeah.
So just to carry on to that, so what about if it's constantly receiving voice, taxi cabs, for instance, and things like that,
Okay.
where the central office is always dispatching and sort of there's almost a constant chatter going on?
Yeah. Well, in this case, you have the option to have a new channel for the data. There are many companies, because I was reading, well, Kenwood says that they recommend up to 70 or 80 users in one channel. If you need more, you can use more channels. For example, they have experience working with 4 channels, 1 for control and 3 for communication, having up to 300 or 350 users. So if you really need users chatting all the time, and you have many devices that you have to receive information, you can use another channel dedicated just for the data. So you can use up to 4
So
channels.
Just dedicate a channel to
Yeah,
your data.
you just escalate up your network,
Thank you.
give more resources. Yeah. Yeah, right.
When you developed your software, did you develop for multiple end stations? Like or you
No.
just develop it this time just for one?
No, I just developed for one. I only had 2 radios, so I only could have 2 sides, and I was reading about that. I think I wouldn't have any issue, because I just have to put identification for each side. That way, I can know if I'm receiving from this side or from the other one. The difference is if I will, and then for each relay I have a special label. For example, relay 1 I'm sending 0 or 1 if I want one on and off. For the relay 2 I send 2 and 3. For the other one 4 and 5 and 6 and 7. So I could have different numbers for the different side. So I don't think will be an issue, but I didn't really test it, and I really focus on have only one remote site. But my idea is that you could have multiple sites and only one base station and control all these sites from this base station. Because also I was using a omnidirectional antenna, and as was giving me 38 kilometers south, it's gonna give me another 30 kilometers north, unless there is some terrain that is blocking me, 30 kilometers west, and 30 kilometers east. Any more questions?
No?
All right, so just a really quick one.
Yeah.
When you started this whole part, what was the actual application that you had in mind?
Okay, so how it started, all these things started as a project for the city of Brandon, where they were gonna purchase a set of digital radios, and then 3 students last year, one was gonna get data from the engine of the bus, the other was gonna send this data using VHF radio, and the other was gonna dump the same data every night using a Wi-Fi hotspot. So my idea was to continue the part of the VHF radio, know if this was possible, try to do some fleet monitoring with the radios, because there are many vehicles that already have this system on it for the voice communication. And why you cannot have like a sensor to know if there is some problem with the driver or if there is some problem with the engine? Yeah, because drivers never report if there is any problem. Yeah, okay, yeah, they just keep going. Maybe there is a alarm that the motor is too warm and they just keep driving. You don't know. So that was the idea. And then I was investigating about that, but I found a company that creates a device that have like accelerometer, can be connected to Wi-Fi, can be connected to satellite, can be connected to cellular network, and also they have like very good interface. They also could send message through. So at that point I realized that you make kind of fleet monitoring system was something that was there and was hard to compete. So I started to think, okay, we have digital communication at large distance. Where else can we use this? And here, like Manitoba, having kind of inspiration, because there are many places where you go a little bit out of the road and you lose all your communication, all your cell phone communication. And what happens if there is something, you have some cattle and you want to control a gate, you have to move to that place. And many people here have VHF systems because of that. So, okay, machine to machine, it's kind of related with our program. So I decided to monitor a remote site with that. Yeah, because you don't really need that much information and it's doable. Okay. Okay. Thank you, everyone.
Back to where it needs to be for the other presentation?